For over a century, people have listened to news, music, and emergency broadcasts using one of the simplest communication technologies ever invented. It is called Amplitude Modulation, or AM. Although modern wireless systems use much more advanced techniques, understanding AM is the perfect starting point for learning how communication systems actually work. In the previous lesson, we learned that modulation transfers information onto a high-frequency carrier, and that different modulation techniques modify different properties of the carrier. The most natural question now is, what does a real modulation system actually look like? Suppose we want to broadcast a person's voice over a long distance. The microphone produces a low-frequency audio signal, but this signal cannot be transmitted efficiently through an antenna by itself. We therefore need a way to place the audio information onto a high-frequency carrier while keeping the information intact. This is exactly the problem that the AM system was designed to solve. It became one of the first practical wireless communication systems and laid the foundation for modern radio communication. An amplitude modulation (AM) system is a communication system in which the amplitude of a high-frequency carrier wave is varied according to the amplitude of the information signal. A basic AM system consists of several major blocks. The information source generates the message, usually voice or audio. The AM transmitter combines this information with a carrier produced by an oscillator. A power amplifier increases the signal strength before the antenna radiates it into free space. At the receiving end, the antenna captures the transmitted signal. The receiver amplifies and filters the signal before a demodulator extracts the original audio information. Finally, a speaker converts the recovered electrical signal back into sound. Intuitively, imagine shining a flashlight whose brightness changes with your voice. The light itself represents the carrier, while its changing brightness carries the information. The light continues to travel normally, but its intensity now contains your message. Physically, consider an AM radio station broadcasting music. The transmitter generates a carrier at a fixed radio frequency, such as 1 MHz. As the music becomes louder or quieter, the transmitter changes the carrier's amplitude accordingly. Thousands of radios can receive this signal simultaneously, each recovering the original music using an AM demodulator. Mathematically, the carrier frequency remains constant, while only its amplitude changes in proportion to the information signal. The receiver detects these amplitude variations and reconstructs the original baseband waveform with relatively simple circuitry. Although AM is no longer the dominant communication method, it remains important in many practical applications. AM broadcasting is still used worldwide for long-range radio transmission because lower frequencies can propagate over large distances, especially at night. Beyond commercial radio, amplitude modulation is also found in aviation navigation systems, some telemetry systems, and educational laboratory experiments. More importantly, AM serves as the conceptual foundation for understanding more advanced modulation techniques, including single sideband, SSB, quadrature amplitude modulation, QAM, and many digital communication systems. For RF engineers, studying AM provides valuable insight into modulation, spectrum generation, transmitter architecture, receiver design, and demodulation principles that appear throughout modern communication engineering. The AM system demonstrates one of the most fundamental ideas in communication engineering. Information can be transmitted simply by changing one property of a carrier wave. This concept remains at the heart of virtually every wireless communication technology developed since. A common misconception is that AM is obsolete, and therefore unimportant. While modern systems rarely use simple AM for high-speed communication, many advanced modulation techniques are direct extensions of the same underlying principles. Understanding AM makes more sophisticated systems much easier to learn. In the next lesson, we will study the FM system and discover how varying the frequency of the carrier, rather than its amplitude, provides much better resistance to noise and higher audio quality. In this lesson, we learned how an AM system transmits information by varying the amplitude of a high-frequency carrier while keeping its frequency constant. We also explored the major building blocks of an AM transmitter and receiver and saw why AM became the foundation of early radio communication. In the next lesson, we will study the FM system and discover how changing the carrier frequency improves communication performance and noise immunity. If you found this useful, like the video, subscribe, and follow for the next lesson.